Hello again. I wanted to help you, Gary. It seems like you was having some confusion in understanding this simple graph. And all it was really with these numbers is how to find the area. Simple geometry it is really. So we established we had this area here, which is this triangle. And you can see that it's a right triangle, meaning one of its angles is a right angle. And this area came about because we were going along the displacement or the movement, the stretch or the compression of the spring along this axis, and the force applied up here. And that was another thing. You were somehow denying that the further we stretch a spring, that there's more force not required. Of course there is, obviously. You know, I mean, I'm not even going to... Anyway. So you get this triangle, and the numbers come about. Well, how do you find the area of this triangle? This triangle represents the work done. And it's very simple, because you can see that because it's a right angle triangle, this square here, if we can find the area of this square, you see, we can then half the area and we'd have the area of this triangle, wouldn't we? So how do we find the area of this square, Gary? Well, let's say that this length here measures 2 units, measurement of 2. And we say that this side has to be, because it's square, has to be another 2. Well, simple geometry. 2 times 2 is 4 to get the area of the square. That's how you do it. So once you've got the area of the square, Gary, you half that area and you get the area of this triangle, you see. Well, half of 4 is 2, isn't it? There. And you see, as we carried on with our extending the spring up here, you see, more force required all the time, obviously. As the spring extends, it needs more and more weight applied to extend it, Gary. Now we've got this area. This is another right angled triangle, Gary, you see. This is another right angled triangle. And if we look, there's a big square here now, Gary. A big square. Now, we want to find the angle of this triangle. If we can find the angle of this, the area of this square, then we can find the area of this triangle, Gary, you see. Well, let's try that, shall we? So this one was a length of 2, so this one's another 2, we can say. So that's one length here is 4. So this would be 4, this side here. So 4 times 4 is 16. Half of 16 is 8, you see. That's where the 8 come from, Gary. That's how you find the area of this big triangle. Okay? I just thought I'd show you that, because that's going to be very useful for you to know basic things like that. The main point of this video is I got a question for you now. You play fair now, because you're constantly demanding that everybody answers your questions. Constantly demanding that people prove it to you. Well, here's a question about you and your fallacy about the conservation of energy. And I'm going to ask you a question. You're always saying, why don't people draw pictures? So I'm going to draw you a picture. It's going to be very basic. It's going to be a stick man. This is a weightlifter, Gary. You've used this analogy quite a lot, but the old weightlifter. And he's got a barbell on the ground in front of him. And he's going to lift this weight up above his head. Like this. Oh no, I've got that wrong. His arms would go like that, wouldn't they? And there's the barbell now, see? Get it in shot. There's the barbell. He's lifted the weight up. Right. Now, I hope you can agree that he's done an amount of work to lift this weight above his head. And we're not going to try and, work out what that weight is. Let's leave the calculations out of it for a minute. This is a conceptual argument. And I'm going to ask a question of you in a minute, a very important one. Now, it's quite right. If this guy was to start lifting this weight and he took all day over it, the time he got it up here, he's used an absolute shed load of energy. I mean, if he survived, he's going to be sweating and he's going to be steams coming out of his ears. He's used a shed load of energy to get that weight up by taking all day over it. But he has done the same amount of work as if he'd lifted it quickly in a clean and snatch or whatever they call it. He's done the same work, but he's expended a hell of a load of energy, Gary. Oh, yes. Now bear with me, my question's coming up to you. And it's a question about the conservation of energy. You deny the conservation of energy for this very good reason. Now, would you agree? Let's establish this first. And obviously you can pause it and say yes or no each time I ask a question. And we can't move on until you do say yes or no. I would hope you would agree that he can lift the weight above his head and he can do it fast or slow. Let's say he's done it, whatever. He's got it above his head now. Now we devise a machine to take this weight and it's going to run a dynamo on its descent with a light bulb here. It's going to generate some power. We've put this weight on a machine. We're going to let it fall to earth. It's going to do work. It's going to, because of its potential energy, because of its force of gravity, it's going to turn the generator and light the lamp. And it's going to expend some energy that we could measure. We could measure the amount of energy that weight has in falling to ground. Do you agree with that, Gary? Do you agree that could be done and we could measure the amount of work done, or if you don't like that language, the amount of energy that we can get out of this falling weight, turning the generator? And we're going to come up with some answer. We're going to come up with some answer. An amount of work, an amount of energy. Okay. Yes or no? Okay. Well, let's assume I'll be kind and I'll say you've said yes. So far, you understand what I'm saying and it makes sense, and you agree. Okay. This is where you go wrong. This is where you say the conservation of energy doesn't hold, because you say that this guy, by lifting the weight quicker, he does the same amount of work, but he expends less energy. Now at this point we're getting the same amount of energy every time by him lifting the weight up and then letting it fall on the machine. Now what happens when he keeps lifting the weight slightly quicker each time, using less energy, drawing the same energy on? Quick, less energy, same energy. Do you not see a conundrum here? There's going to come a point when he can use less energy by lifting the weight than he can retrieve from it turning the dynamo. Now what do you say to that, Gary? How do you get around that? At what point stops him lifting the weight and expending less energy than he can get from dropping it on the machine? And what are you going to say? What are you going to say? This is why the conservation of energy holds, because by your thinking, we would have free energy. You cannot get around it. This amount of work is the same amount of work every time, no matter how fast or slow he lifts it. It has to be the same amount of work because we get this amount of work here after dropping the weight. It has to be the same. If it didn't, we'd have a free energy machine. So what you going to say? Yes, he can use less energy up to a point, and then there's a point where, you know, it's going to be the same amount of energy no matter how fast he does. I don't know. But I want you to answer this, Gary. Stop turning it around. Stop claiming this is not on the question, which you usually do. This is the question you've been addressing. This is the example you've been using. And I want an answer from you. Thank you.